the solar system still holds worlds we barely understand. Among them is Uranus, a pale blue planet drifting nearly 3 billion kilometers from the Sun. For centuries it has existed mostly as a distant point of light in telescopes, quiet, cold, and largely ignored. But in recent years, scientists have begun asking a question that could rewrite what we think this planet actually is. What if Uranus is not an ice giant at all? In 2025, planetary scientists Luca Morf and Ravit from the University of Zürich published a study in the journal Astronomy and Astrophysics that challenged a long-standing assumption about the planet's interior. Using thousands of computer simulations, they tested how different combinations of rock and water inside Uranus would affect its gravity, size, and observed properties. Instead of confirming the traditional model, their results opened a surprising possibility. Uranus may contain far more rock than scientists ever expected. To understand why this matters, imagine trying to determine the ingredients of a sealed metal sphere simply by measuring its weight and how it moves through space. Scientists cannot drill into Uranus or see beneath its clouds. Instead, they rely on indirect clues: the planet's mass, its radius, its gravity field, and the faint signals captured during a brief spacecraft flyby decades ago. From those clues, researchers build models of what might exist deep inside. For decades, those models painted a fairly clear picture. Uranus was thought to contain a small rocky core buried beneath enormous layers of water, ammonia, and methane, materials scientists loosely grouped together as planetary ices. That classification gave Uranus its place among the solar system's ice giants alongside Neptune. But the new simulations suggested something far less certain. When the researchers allowed the interior composition to vary freely, the results showed that Uranus might contain anywhere from almost no rock at all to a structure dominated by rocky material. In the most extreme cases, the planet could be closer to a giant rocky world wrapped in gas rather than an ice-rich planet. If that interpretation holds true, it would not just change how we understand Uranus. It could reshape theories about how entire classes of planets form, including thousands of similar worlds already discovered around other stars. Yet this possibility raises an obvious question. How did scientists become so unsure about a planet that has been known for more than 2 centuries? The answer begins with the only time humanity has ever visited Uranus. For more than 2 centuries after its discovery, Uranus remained an enigma. Astronomers could measure its orbit and observe its faint turquoise glow, but the planet itself refused to reveal much more. Then, in the mid-1980s, a robotic explorer changed everything. In January 1986, NASA's Voyager 2 spacecraft swept past Uranus during a carefully planned flyby. It had already visited Jupiter and Saturn, but Uranus was something different. No spacecraft had ever seen this distant world up close. Scientists would have only a few hours to gather data before the probe continued its journey into the outer darkness of the solar system. As Voyager approached, its instruments began transmitting the first detailed measurements ever taken of the planet. Cameras captured a smooth blue-green globe wrapped in a pale atmosphere. Spectrometers analyzed the gases in the upper clouds. Magnetometers measured the invisible magnetic field surrounding the planet. Each instrument was designed to extract clues from a world no human had ever studied directly. Almost immediately, the data produced surprises. The spacecraft discovered 11 previously unknown moons orbiting Uranus. It confirmed a system of narrow rings circling the planet. But one result stood out above all others. Temperature readings from the atmosphere revealed something extraordinary. Uranus was colder than scientists expected. Far colder. Measurements showed that the upper atmosphere dropped to about -224 degrees Celsius. That made Uranus the coldest planetary atmosphere anywhere in the solar system. Even Neptune, which orbits farther from the Sun, appeared warmer by comparison. At first glance, this seemed puzzling, but the problem went deeper. Giant planets usually release heat left over from their formation. Jupiter and Saturn still glow faintly with internal energy, like objects slowly cooling after being heated long ago. Uranus, however, seemed almost silent in comparison. It radiated very little excess heat into space. This raised a troubling possibility. Something inside Uranus was behaving differently from every other giant planet scientists had studied. Voyager also revealed another strange feature. The planet's magnetic field was dramatically tilted and shifted away from the center of the planet. Instead of emerging neatly from the core, the field appeared distorted and lopsided, as if the engine generating it was located somewhere unexpected inside the planet. By the time Voyager 2 disappeared into the darkness beyond Uranus, researchers had gained only a brief glimpse of the planet, yet that glimpse left them with more questions than answers. Why was Uranus so cold? Why was its magnetic field so unusual? And most importantly, what was really hidden beneath its thick atmosphere? For decades, scientists believed they already knew the answer. Uranus, they said, was simply an ice giant. But that assumption would eventually begin to unravel. For decades after Voyager 2's flyby, scientists believed the mystery of Uranus had already been solved. The planet, they concluded, belonged to a special category known as an ice giant. In textbooks and scientific papers, Uranus and Neptune were grouped together as worlds built largely from substances astronomers called planetary ices. But the term was always a little misleading. In everyday language, ice suggests something frozen and solid. Inside Uranus, nothing could be further from the truth. Deep beneath the blue clouds, pressures climbed to hundreds of billions of times stronger than the air pressure at Earth's surface. Temperatures rise to several thousand degrees Celsius. Under those conditions, water, ammonia, and methane do not form ordinary ice. Instead, they behave more like a dense, superheated ocean compressed beneath layers of gas. The traditional model placed a relatively small rocky core at the center of the planet. Surrounding that core would be a massive mantle of these exotic fluids, with hydrogen and helium forming the outer atmosphere. The structure seemed reasonable because it matched the limited measurements available from Voyager 2 and Earth-based observations. But the explanation depended on a fragile assumption. Scientists were trying to describe the inside of a planet they had never actually seen. To understand how uncertain this can be, imagine hearing the sound of an engine inside a sealed machine, but never being allowed to open the casing. Engineers might estimate what components are inside based on the noise, the vibrations, and how much energy the machine produces. Yet several very different designs could produce similar external signals. Planetary scientists face a similar challenge with Uranus. They cannot drill through its clouds or send instruments deep into its interior. Instead, they rely on indirect clues: the planet's mass, its size, the way gravity behaves around it, and faint signals collected during that brief Voyager encounter in 1986. Through the 1990s and early 2000s, these clues appeared consistent with the ice giant model. Uranus seemed to contain enormous amounts of water and other volatile materials, enough to justify the name. But a growing number of researchers began to notice something unsettling. The available data did not uniquely support that picture. In fact, multiple very different internal structures could produce the same measurements scientists were observing. And that realization meant something important. The widely accepted description of Uranus might not be a confirmed fact at all. It might simply be the most convenient guess. As computational models became more powerful in the decades that followed, planetary scientists began revisiting the problem with fresh tools and new methods. And what they would soon uncover suggested that Uranus might be hiding a very different interior than anyone expected, an interior that could challenge the very definition of an ice giant. Something about Uranus does not add up. When scientists compare the giant planets of the solar system, a clear pattern usually appears. Massive worlds hold on to enormous amounts of heat left over from their formation billions of years ago. That heat slowly escapes into space, stirring their atmospheres and powering violent weather systems. Jupiter glows with internal energy. Saturn does the same. Even distant Neptune releases more than twice the energy it receives from the Sun. Uranus does not follow that rule. Measurements collected since the 1986 flyby of NASA's Voyager. 2 spacecraft revealed that Uranus radiates only about 15% more energy than it absorbs from sunlight. In planetary terms, that is almost nothing. It means the planet is barely releasing its internal heat at all. This discovery puzzled scientists for decades. If Uranus formed in the same chaotic environment as the other giant planets, it should still contain enormous reserves of trapped heat deep inside. Yet the planet behaves almost as if that energy has been locked away somewhere beneath its clouds. By the early 2000s, researchers began examining the problem more closely. Observations from telescopes such as the Keck Observatory in Hawaii and the Hubble Space Telescope allowed scientists to monitor Uranus's atmosphere over many years. The results confirmed that the planet's weather systems were far less energetic than those on Jupiter, Saturn, or Neptune. In simple terms, Uranus behaves like a giant world that has been insulated from the inside. Imagine a furnace sealed inside a thick container that prevents most of the heat from escaping. From the outside, the surface would appear cool and quiet, even though enormous energy remained trapped within. Planetary scientists began wondering whether something similar had happened inside Uranus long ago. In 2018, a team of researchers led by planetary scientist Jacob Kegereis at Durham University used high-resolution computer simulations to investigate a dramatic possibility. Their work, published in the Astrophysical Journal, explored what might happen if a young Uranus had experienced a massive collision during the early history of the solar system. The simulations suggested that roughly 3 to 4 billion years ago, Uranus may have been struck by an object 2 to 3 times the mass of Earth. The impact would have lasted only a few hours, but the consequences could have reshaped the planet forever. Such a collision could tilt Uranus onto its side, explaining the planet's unusual 97-degree axial tilt. But the models also revealed something even more intriguing. Much of the impactor's material could have mixed into Uranus's interior, forming a chaotic layer that traps heat deep within the planet. If that scenario is correct, the strange coldness of Uranus may not be a mystery at all. It may be the fossil record of a violent ancient collision. And if a massive protoplanet truly merged with Uranus billions of years ago, it raises a much deeper question. What exactly did that collision leave behind inside the planet? Billions of years ago, the young solar system was not a calm place. Planets were still forming, and enormous bodies of rock and ice moved through unstable orbits. Collisions were common, some created moons, others reshaped entire worlds, and according to modern simulations, Uranus may carry the scars of one of the most dramatic impacts in planetary history. In 2018, planetary scientist Jacob Kegereis and his colleagues at Durham University ran a series of detailed computer simulations designed to recreate Uranus as we see it today. Their goal was simple: test whether a giant collision could explain the planet's unusual tilt and strange internal behavior. The results, published in the Astrophysical Journal, pointed to a remarkable scenario. The models showed that roughly 3 to 4 billion years ago, Uranus may have been struck by a protoplanet 2 to 3 times the mass of Earth. This was not a direct head-on collision. Instead, the impact likely occurred at a shallow angle, more like a glancing blow than a direct crash. Even so, the energy involved would have been extraordinary. In only a few hours, the force of that encounter could have tipped the entire planet onto its side. That alone would explain Uranus's extreme axial tilt of about 97 degrees, which causes the planet to roll through its orbit rather than spin upright like most worlds. But the simulations revealed something even more important. A large fraction of the impacting body would not have escaped into space. Instead, much of its material would have plunged deep into Uranus, mixing with the planet's interior and forming a chaotic layer rich in heavy elements. The researchers describe this layer as high-entropy material, matter that is extremely hot, disordered, and inefficient at transporting heat. In simple terms, it behaves like insulation. Imagine wrapping a thick blanket around a heater. The heater still produces energy, but the warmth struggles to escape. According to the simulations, the debris from this ancient collision could form exactly that kind of insulating barrier inside Uranus. Heat produced deep within the planet would remain trapped beneath the layer rather than rising freely toward the atmosphere. This could explain why Uranus appears unusually cold and quiet compared with the other giant planets. But the consequences of such a collision would not stop at heat flow. If a massive protoplanet merged with Uranus, it would also deliver an enormous amount of rocky material into the planet's interior, and that possibility leads to an even more provocative idea. What if the collision did more than tilt Uranus? What if it fundamentally changed what the planet is made of? In planetary science, sometimes the most surprising discoveries come not from new spacecraft, but from new ways of looking at old data. Nearly 4 decades after Voyager 2 flew past Uranus, scientists are still extracting new insights from the measurements it collected during those few hours in 1986. In 2025, planetary scientists Luca Morf and Ravit at the University of Zürich revisited one of the biggest unanswered questions about the planet: what exactly lies inside Uranus? Their study, published in the journal Astronomy and Astrophysics, used a method that deliberately avoided one of the biggest pitfalls in planetary modelling, starting with assumptions. For years, most models of Uranus began with a familiar structure: a small rocky core at the centre, surrounded by thick layers of water, ammonia, and methane. Those materials were grouped together under the label planetary ices, which is why Uranus and Neptune became known as ice giants. But Morf and Heled chose a different strategy. Instead of deciding in advance what Uranus should look like on the inside, they generated thousands of possible interior structures using powerful computer simulations. Each model contained different proportions of rock, water, and other materials. The models were then tested against the real measurements scientists have of Uranus: its mass, its size, its gravitational behavior, and other observable properties. Think of it as solving a puzzle by trying every possible arrangement of pieces until only the combinations that fit the picture remain. What the researchers found was unexpected. The range of possible compositions inside Uranus turned out to be far broader than scientists had previously assumed. In some of the models, the planet contained very little rock at all, but in others, the amount of rocky material was dramatically higher, enough that rock could dominate much of the interior. This result introduced a possibility that had rarely been considered before. Uranus might not be an ice giant in the way scientists traditionally imagined. Instead of a world dominated by exotic fluids like water and ammonia, it could be closer to a massive rocky planet surrounded by thick layers of gas and volatile material. If true, that would represent a fundamentally different type of planet, something that planetary scientists sometimes describe as a rock giant. The idea remains uncertain. The current measurements of Uranus are still limited, and several different internal structures remain possible. But the simulations demonstrated something crucial. The traditional picture of Uranus as a water-rich ice giant is not the only explanation that fits the data. And once that assumption began to crack, scientists started looking at the planet in a very different way. Because if Uranus truly contains far more rock than expected, the consequences extend far beyond a single planet in our solar system. They may reshape how scientists interpret thousands of distant worlds already discovered orbiting other stars. To understand why, we have to look beyond Uranus itself, and into the rapidly growing field of exoplanet discovery. If Uranus turns out to be a rock giant, the discovery would not only change the story of one distant planet, it would change how scientists interpret an entire class of worlds scattered throughout the galaxy. In the early 1990s, astronomers confirmed the first planets orbiting stars beyond our Sun. Since then, observatories such as NASA's Kepler Space Telescope have transformed planetary science. Thousands of exoplanets have now been identified, revealing that planetary systems are far more diverse than scientists once imagined. Among these discoveries, one category appears again and again: planets slightly larger than Earth but smaller than Jupiter. Many of them fall into a size range remarkably similar to Uranus and Neptune. According to data released by NASA's Kepler mission in the 2000s, worlds roughly 2 to 4 times the size of Earth are among the most common planets in the Milky Way. Yet our own solar system contains only 2 examples of this category: Uranus and Neptune. For years, astronomers assumed these distant worlds were similar to our ice giants. The reasoning seemed simple. If Uranus and Neptune are dominated by water-rich interiors, then planets of similar size elsewhere might share the same structure. But the new interior models of Uranus suggest the situation may not be so straightforward. If Uranus contains far more rock than previously thought, then many of those distant planets may have been misclassified. Instead of being water-dominated ice giants, some could be massive rocky worlds wrapped in thick atmospheres. To understand why this matters, imagine trying to identify a distant island by the silhouette of its mountains. From far away, several landscapes might appear almost identical, even though their geology is completely different. In planetary science, mass and radius measurements provide a similar outline. They reveal the size of a planet and how heavy it is, but they do not always reveal the exact materials hidden inside. Uranus may be teaching scientists an important lesson. Two planets with nearly identical sizes can still be built from very different ingredients. That realization carries enormous implications for the search for habitable worlds. If astronomers have misunderstood the composition of Uranus-like planets, it could mean that the diversity of planetary interiors across the galaxy is far greater than current models predict. And that possibility brings the focus back to our own solar system. Because before scientists can confidently interpret the thousands of distant planets they observe today, they must first solve the mystery much closer to home. What is Uranus truly made of? For a long time, Uranus looked almost lifeless. When Voyager 2 sent back the first close images in 1986, the planet appeared as a smooth blue sphere with almost no visible weather. Compared with the swirling storms of Jupiter or the turbulent clouds of Neptune, Uranus seemed strangely quiet. Many scientists began to think the planet was meteorologically inactive, a frozen giant drifting silently through space. But decades later, new telescopes began to reveal a very different picture. In 2014, astronomers using the Keck Observatory in Hawaii detected something remarkable in infrared images of Uranus. A series of enormous storms had erupted across the planet's northern hemisphere. One of these storms reflected nearly 30% of the planet's total light at that wavelength, making it the brightest atmospheric feature ever observed on Uranus. For the first time, even amateur astronomers using smaller telescopes could see atmospheric activity on the distant planet. The discovery forced scientists to reconsider a long-standing assumption. Uranus was not quiet at all. Its storms had simply been hidden in wavelengths that earlier instruments could barely detect. At the same time, long-term observations from the Hubble Space Telescope began tracking how the planet's atmosphere changed over time. By studying images taken between 2002 and 2022, researchers observed dramatic shifts in the haze and cloud patterns near Uranus's poles. These changes followed the planet's unusual seasons. Because Uranus is tilted by almost 98 degrees, each pole spends decades pointed toward the Sun. During this slow seasonal cycle, sunlight alters the chemistry of the upper atmosphere, thickening aerosols and changing how clouds form. But Uranus hides another mystery, even stranger than its storms. During the Voyager 2 flyby, instruments measuring the planet's magnetic field revealed that it behaves unlike any other magnetosphere in the solar system. Instead of emerging from near the planet's center, the magnetic field is tilted by about 59 degrees and shifted far from the core. This misalignment causes the magnetic field to wobble and twist as the planet rotates, producing complex auroras that appear in unexpected locations across the atmosphere. In 2023, astronomers using the Keck 2 telescope finally detected infrared auroras on Uranus after decades of searching. These glowing patterns provided new clues about the strange magnetic environment surrounding the planet. Taken together, these discoveries reveal a world that is far more dynamic than the quiet sphere Voyager first photographed, and each new observation adds another piece to the puzzle of what lies hidden deep inside Uranus. Because the storms, the seasons, and even the planet's distorted magnetic field may all be connected to the same questions scientists are still trying to answer. What kind of planet is Uranus really? Uranus does not travel through space alone. Surrounding the planet is a complex system of moons and rings, silent companions that may preserve the evidence of a catastrophic event billions of years in the past. Today, astronomers have identified 29 moons orbiting Uranus. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were first observed in the 19th century, long before any spacecraft had visited the distant planet. But when NASA's Voyager 2 spacecraft flew past Uranus in January 1986, its cameras revealed that these moons were far from simple frozen spheres. Miranda in particular shocked scientists. Its surface appeared shattered and rearranged, covered with enormous cliffs and strange patchwork terrain, unlike anything seen elsewhere in the solar system. Some of its cliffs plunge more than 20 kilometers high, among the tallest known geological structures on any planetary body. Planetary scientists began to suspect that something dramatic had once disturbed the Uranian system. More recent studies have only deepened that suspicion. Research published in 2025 suggests that several of Uranus's major moons may contain internal oceans hidden beneath thick shells of ice. If true, these moons are not just frozen relics. They may still be evolving worlds with active interiors. The rings of Uranus tell another part of the story. Unlike Saturn's bright rings, Uranus is surrounded by thin, extremely dark bands of debris. Their reflectivity is less than 2%, making them some of the darkest known structures in the solar system. Astronomers believe these rings may have formed when a small moon was shattered by a collision long after the planet itself formed. But the rings also preserve clues about Uranus's unusual orientation. Because the planet rotates on its side, the rings circle Uranus like a tilted target in space, perfectly aligned with the planet's sideways axis. This strange geometry may be a lingering signature of the ancient collision scientists believe tipped the planet over. If a massive protoplanet truly struck Uranus billions of years ago, the debris from that event could have reshaped the entire system, altering the planet's interior, tilting its rotation, and scattering material that eventually formed moons and rings. In other words, the satellites of Uranus may be witnesses to the same violent moment that changed the planet forever. Yet despite everything scientists have learned, the most important evidence may still be hidden deep beneath Uranus's clouds. To uncover it, humanity may need to return to the planet itself, and plans to do exactly that are already beginning to take shape. There is a planet in our solar system that may have been misunderstood for more than 2 centuries. Uranus was discovered in 1781 by astronomer William Herschel. Since then, it has completed less than 3 full orbits around the Sun. In all that time, humanity has visited it only once. The Voyager 2 spacecraft flew past the planet in January 1986, collecting a few hours of data before continuing toward the edge of the solar system. Yet those few hours revealed a world unlike any other. A planet tipped onto its side, a magnetic field tilted and displaced from its center, an atmosphere colder than any other planetary atmosphere known. For decades, scientists believed they understood the basic explanation. Uranus was classified as an ice giant, a planet dominated by water, ammonia, and methane deep inside. But recent research has reopened the question. In 2025, planetary scientists Luca Morf and Ravit of the University of Zürich published new interior models in the journal Astronomy and Astrophysics. By testing thousands of possible structures, their simulations showed that Uranus might contain far more rock than earlier theories predicted. In some models, rocky material dominates the planet's interior rather than water-rich layers. If this interpretation is correct, Uranus may represent a completely different category of planet, something closer to a massive rocky world hidden beneath a thick atmosphere, a rock giant. The implications reach far beyond our solar system. Observations from NASA's Kepler mission and other exoplanet surveys show that planets roughly the size of Uranus are among the most common in the Milky Way galaxy. Understanding the true nature of Uranus could therefore reshape how scientists interpret thousands of distant worlds. But there is a problem. The data we have is still limited. Without direct measurements of the planet's gravity field, atmospheric chemistry, and internal structure, several competing models remain possible. The true composition of Uranus is still uncertain. That is why planetary scientists are now looking toward the future. In the 2023 to 2032 Planetary Science Decadal Survey, the United States National Academies identified a dedicated Uranus orbiter, an atmospheric probe, as the highest priority mission for exploring the outer planets. Proposed launch opportunities around 2031 and 2032 could allow a spacecraft to use Jupiter's gravity to shorten the journey. Such a mission would map the planet's gravity and magnetic fields, probe the atmosphere, study its moons, and search for the signatures hidden deep inside the planet. For the first time, humanity could directly test whether Uranus truly belongs among the ice giants, or whether the sideways world at the edge of our planetary neighborhood has been something else all along.